All right, 1720, here we go again, Chapter 8, Section 4, welcome back. All right, we're going to do DeMoivres' Theorem and powers and roots of complex numbers. Okay, so here's DeMoivres' Theorem here. If we have a complex number in the form given here, r cosine theta plus I sine ri sine theta, okay, we can take the power here, the exponent. So if we're given r times the quantity of cosine of theta plus I sine theta, r raised to the power of n, all right, that translates over to r to the n times cosine of n theta plus I sine n theta. So this is the theorem for if we have a complex number with an exponent. There's what it looks like in compact form, which you might see on your homework assignment. Okay, so let's take a look at this one. We want to find 1 plus I squared roots of 3, all raised to the 8th power. And we want to express the result in rectangular form. Okay, so a couple steps to do in these problems, just so we recognize, all right, the exponent's 8, so that's going to make a difference for us, but it's important that we express this in trig form first, okay? So we're going to write 1 plus I squared roots of 3 in trig form. So when we do that, we get 2 times cosine of 60 plus I sine of 60. So just in case you forgot, where does that come from? Well, the 60, remember, that comes from tangent. All right, so we have tangent of the vertical over the horizontal, so it's tangent of square root of 3 over 1. All right, so it's tangent inverse of that technically, and that's how we get the 60. We know that it's a 1 square root of 3, 2 triangle, so it's 60 degrees. That's where the 60 comes from. And then we have to find the magnitude, right? So you're going to take 1 squared plus square root of 3 squared, and then square root your answer. That's where the 2 comes from. So there's getting everything back into trig form for us to do this, okay? Now we're not done yet. All we did was take the 1 plus I square roots of 3 into trig form. Now we're going to use DeMoivres' theorem. Okay, so when we rewrite it, okay, we're going to use DeMoivres' theorem. It's going to be 2 times cosine of 60 plus I sine of 60, all raised to the 8th power. Now that 8's going to come into play. If we just follow the substitution that we saw for the theorem, okay, we're going to get a 2 to the 8th times the quantity of cosine of 8 times 60 plus I sine of 8 times 60. So when we do the math here, 2 to the 8th is 256. All right, 8 times 60 is 480, so we're going to have cosine of 480 plus I sine of 480. Now that's not an easy angle to work with, but we can find its coterminal. If you remember doing that back in like chapter 1, chapter 2, right? Angles that end in the same location. So we can take 480 and subtract 360 from it, and we end up getting 120. So 120 is coterminal with 480. Hopefully you guys remember those terms. All right, and now 120 is an easier angle for us to work with. Okay, now we just simplify everything down. So we know that cosine of 120 is negative 1/2, right? Because 60 degrees is the reference angle, and it's in the second quadrant, so cosine is negative. All right, and same with sine, except for sine is not going to be negative there. Sine will be positive there. Using the same angle, right? Same same reference angle of 60 degrees gets 120, gets the square root of 3 over 2. All right, then we can just factor out a 2 in the denominator. So we're going to have 256 divided by 2, which is 128. You can also factor out the negative value, but it really won't change much for us. But we end up with negative 128 plus 128 I square roots of 3. So that's putting it back in rectangular form. Okay? Hopefully, you guys, these aren't really too bad. So what we have to do first, we have to put it in to trig form, then apply DeMoivres' theorem, and then simplify everything down, and we're in rectangular form. All right, so take a look at this for the nth root. All right, so we just did to the 8th root, but the complex number a plus bi is an nth root of the complex number x plus yi if a plus bi to the n equals x plus yi. Alright, this will make more sense as we kind of work through a numerical example. Alright, here's what all that means though. So, nth root theorem, this is the theorem for finding, like, we just did powers, alright, so now we're doing this root theorem, so square root, cube root, those sort of things. So we can see that we're going to get something of the form the nth root of r. So that would be like the 4th root of r, or the 5th root of r, or the 3rd root of r, or even the square root of r. Okay, so we can end up writing that is the nth root of r times cosine of alpha plus I sine of alpha. And you can see how to write it in shorter form, but we have to know how to calculate alpha. Okay, alpha is going to be theta plus 360 times k divided by n. K is going to be our constant. Alright, n is going to be the root that we're going to be asking to find. Alright, so when we substitute into all of this, that's how it's going to go down. Okay, the nth root theorem is thetas and radians is going to look like this. Alright, theta plus 2 pi k over n. Okay, remember k is still the constant that we're changing, n is still the root. Those parts don't change, but we're just going to use 2 pi instead of 360. So just the difference if we're in radians versus degrees, nothing absolutely new here. Alright, so we want to find the 2 square roots of 4i. We'll write the roots in rectangular form. Okay, so we got to find the square roots of 4i. So our best bet is to put this into trig form first. Alright, so rectangularly we're sitting at 0 plus 4i. So we have to think about, what value makes cosine go to 0. So you should be thinking about, pi over 2 or 3 pi over 2 or an answer like that. But we have to make sure that it works out so that the sine value is positive in this case. So a good approximation for us would write this as 4i is equal to 4 times cosine of pi over 2 plus I sine of pi over 2. We're choosing pi over 2 because cosine of pi over 2 is 0 and sine of pi over 2 is 1, and we need to have it equal 4i. So in order for that to happen, r needs to be 4 in this case. So that's where all those values come from. So r is 4 and theta is now pi over 2. Now we're going to solve for alpha. Okay, so we want to find the square roots. They have an absolute value, right? Now square root of 4 is 2. And here's our argument. Since we're in radians, we're going to take alpha is equal to pi over 2. Okay, that's just our theta divided by 2. Okay, that's with k because that's our root, or n, I'm sorry, is 2 because that's the root we're looking for. Alright, and k is for any nth root here. So we're going to end up with pi over 2 divided by 2 plus 2 pi k divided by 2. That's going to equal pi over 4 plus pi k. So that's our alpha in this case. Okay, so there's 2 square roots. We're going to let k equal 0 and k equal 1 because there's 2 square roots. Alright, when we find that. So if k is 0, okay, alpha is going to equal pi over 4 plus pi times 0, which is just pi over 4. If k is 1, okay, alpha is going to be pi over 4 plus pi times 1. Alright, and then we have to change pi into 4 pi over 4. So we end up getting 5 pi over 4 for our alpha. Okay, so our 2 roots, okay, consist of that. So if we rewrite them in the short form, we're going to get 2 CIS of pi over 4 and 2 CIS of 5 pi over 4. Okay, relatively simple. We just got to keep track of how many roots we're doing it for. So if it was a 3rd root, we'd make k equals 3 and solve the same thing that we've been doing. Okay, and just get our answers. Nothing too complicated about this one. Okay, now the last part asks us to put it back into rectangular form. This is trig form. So we need to rewrite each one of these expressions in terms of r and cosine and sine. Okay, So the first one, all right, it becomes 2 times cosine of pi over 4 plus I sine of pi over 4. And pi over 4, right, that's our 45. So that's a 1 square root of 2 triangle that you need to solve. So that's where the square root of 2 over 2 comes from for each one of these. And then we're going to have 2 times the quantity square root of 2 over 2 plus I square root of 2 over 2. We can factor a 2 out of the denominator, and it's going to cancel with the 2 in the numerator, so we end up with square root of 2 plus I square root of 2. Alright, that's just for the one root, and then we have the other root that we have to use doing the same math. I'm not going to talk you through it. It's 5 pi over 4 is the other angle in question there. Works the same way we did the first part. You should be able to solve those triangles and get those values. Okay. Alright, let's do example 3 here. We want to find all fourth roots of negative 8 plus 8i square root of 3. We're going to write the roots in rectangular form at the end. So, first thing, we have to write it in its trigonometric form. Okay, so we're paying attention. We have to calculate r, so we're going to have to do negative 8 squared plus 8 square roots of 3 squared. So when we do that, we get the square root of 256, which is 16. So r is 16. And then we have to do tangent. So it's 8 square roots of 3 over negative 8. The 8 and negative 8 cancel. So tangent is equal to negative square root of 3. When all is said and done, you should be able to do that. It's negative square root of 3 over 1. Alright, so we should know that that puts us in the second quadrant. Alright, and we should know that that gives us a reference angle of 60. And with the reference angle of 60, we know that theta is going to be 120 there. So that's all stuff from, first and second chapter, maybe into the third that we've been doing. Okay, so once that simplifies down, you have negative square root of 3 over 1. That's what you're using there, and then you're using the 1 square root of 3 2 triangle to solve, but that tells us the reference angle is 60, so we get 120. Okay, so now we go into our long form. We're going to find the fourth root, so we're going to substitute that into the root formula, but now that we know that r is 16 and theta is 120. Okay, so we write that out as 16 cosine of 120 I sine of 120 when we do this. Now we bring up our alpha, and we know the fourth root of 16 is 2. Alright, that's the I'm going to call it the real piece, but it's the magnitude piece. Alright, the square root of 16, or the fourth root of 16 is 2. Now we have to find the fourth root using alpha. Okay, so we have 120 degrees divided by 4. Okay, so that's our 120 over n, right? Plus, we are in degrees with this one, so we're going to take 360 times k over 4. Alright, so we end up getting 30 plus 90 times k. Okay, so that ends up being 120k for alpha. Then we have to substitute, since there's 4 roots, we don't substitute 1, 2, 3, and 4. We always start at 0. And we do 0, 1, 2, and 3. Those are going to represent the 4 different roots. Okay, so if k is 0, alpha is going to be 30 plus 90 times 0, which gives us 30. If k is 1, alpha is going to be 30 plus 90 times 1, which is 120. If k is 2, okay, alpha is going to be 30 plus 90 times 2, which is 210. And if k is 3, alpha equals 30 plus 90 times 3. Alright, so that's 270 plus 30, which is 300. Okay, so we're going to use all these values in finding the roots. So this is in shorthand. You should see that it's 2CIS 30, 2CIS 120, 2CIS 210, and 2CIS 300. Okay, so we have to find the roots for all of those. I'm not going to walk you through this one too much. You should be able to kind of follow on. We did a previous example, but a lot of it is just, now it's just doing stuff we did in chapters 1, 2, and 3. I think you guys should be able to solve each one of these. So if we get 2CIS 30, it ends up being the square root of 3 plus I. For 2 CIS 120, it ends up being negative 1 plus I root 3. For 2 CIS 210, it ends up being negative square root of 3 minus 1. And for 2 CIS 300, it ends up being 1 minus I square roots of 3. You guys should know by now how we calculate all those values, alright, and where they come from. Okay. So if we were to graph all these, just remember the real axis is the horizontal axis and the imaginary axis is the y-axis, as we take a look. Okay, but that's a solution if we were to graph all of these out. Alright, example 4, we're going to solve an equation with complex roots. Alright, so we want to find all complex number solutions of x to the 5th minus I equals 0. We're going to graph them as vectors in a complex plane. Alright, so deeming, real is in the x and imaginary is in the y part of the plane. Okay, so first step, we got to solve for x, right? So x to the 5th equals 1. We're just solving that through. There's only one real solution, but there's 5 complex solutions. Okay, one real solution, 5 complex solutions. Okay, so write 1 in trig form. Okay, so if we have that, we have 1 plus 0i. We're literally taking the number 1. It's just the real component, and there's no imaginary component, so we're writing 1. Okay, in trig form, it's 1 plus 0i. Then we have to find r, so it's 1 squared plus 0 squared square rooted, so r equals 1. Then we have to find tangent. Tangent is 0 over 1, which is 0. So r is 1, okay, and tangent of theta is equal to 0 degrees when we do this. So when we simplify this out, okay, we're going to write this as 1 equals 1 cosine of 0 plus I sine of 0. Then we're going to use the 5th roots, okay? So taking a look at the top part, we're going to take the 5th root of 1, which is 1, and then we have to do the arguments, which is alpha. So we're going to get 0 divided by 5, because we're looking for the 5th root, plus 360 times k divided by 5. So when it's all said and simplified, we're going to do 0 plus 72 times k, or just 72k now. So since we're doing the 5th root, we have to substitute in k of 0, 1, 2, 3, and 4. Okay, so when we substitute that in, when k is 0, alpha is going to be 0. When k is 1, alpha is going to be 72. If k is 2, alpha is going to be 144. If k is 3, alpha is 216. And if k is 4, alpha is going to be 288 degrees. So that's substituting in their k values. You'll always know k is always going to be whatever root that the problem asks you to find. Okay, so there's our solution set in the shorthand. Alright, and if we work through them just like we did the other ones, okay, this is graphing them. Okay, you can use your calculator to get the values. Cosine of 72 is not an easy one. Cosine of 0 and sine of 0, that one should be pretty easy and straightforward. The rest of these, use your calculator. So remember, whatever value we get, okay, you're making sure that all students take calculus, ending up in the correct quadrant when you do this. Alright, make sure your calculator's in degree mode, and remember that the x-axis is the real, so that's your cosine piece that you're graphing, and then your imaginary axis is your imaginary, or is the y-axis, and that's the sine piece that you're graphing when you do these. So essentially, that's where they all work out to be. Okay, so you need to type in like cosine of 144 in your calculator. That'll give you a negative answer. Okay, and then you'll have sine of 144 that's going to give you a positive. Okay, so that's how we're going to draw out those vectors. You guys should be able to do all that. Just get the values using your calculator. Alright, that's the end of this section. If you guys have any questions, go ahead and email me or ask me to team meet or Zoom meet or whatever you guys need help with on this one. Else, the rest of you guys, I will see you in class. Take it easy.